Hi everyone, welcome back to PRAKASAM tutorials. In my previous video, we have discussed about concept of characteristic function. Now here in this video, I am going to discuss about properties of characteristic function. There are some important properties of the characteristic function that are, first one is the maximum magnitude of the characteristic function is unity. That is, magnitude of pi x of omega is less than or equal to 1. So this one is already explained in the concept of characteristic function. And second property is maximum value of the magnitude of the characteristic function is at omega is equal to 0 and the maximum value is 1. So this is also derived and also explained in the concept of characteristic function. And third property is if the characteristic function of two random variables are identical, then the random variables are said to be identical distribution, that is they are of identical density. So this is the third property. And fourth property is if pi x of omega is the characteristic function of a random variable capital X, then the characteristic function of the random variable y ax plus b is e power j omega b into pi x of a omega. Prove this property. Coming to the proof, so we know that the definition of the characteristic function of a random variable is pi x of omega is equal to expectation of e power j omega x. So now we want to prove that characteristic function of the random variable ax plus b is this one. So similarly, the characteristic function of the random variable y is pi y of omega is equal to expectation of e power j omega y. Now here y is ax plus b. Substitute y is equal to ax plus b into on RHS side of this equation. We get pi y of omega is equal to expectation of e power j omega into ax plus b. Multiplying j omega into within the bracket term, we get expectation of e power j omega x into e power j omega b. So expectation of ax is equal to a expectation of x, that is the property of the expectation. So using property of expectation of this RHS term is written as e power j omega b into expectation of j into expectation of e power j omega a into x. So using definition of the characteristic function, expectation of e power j omega a x is pi x of omega, pi x of omega a. So therefore, pi y of omega is equal e power j omega b into, so this value is from the definition of the characteristic function pi x of a omega. Next property is if pi x of omega is the characteristic function of a random variable, then the characteristic function of the random variable y is equal x plus a by b, where a and b are the constants. So that characteristic function of the random variable y is equal to x plus a by b is e power j omega a by b into pi x of omega by b. Now here small a and small b are the constant. Now coming to the proof of this property is, so we know that the characteristic function of the random variable capital X is pi x of omega is equal to expectation of e power j omega x. Similarly, the characteristic function of the random variable capital Y is pi y of omega is equal to expectation of e power j omega y. Now here we want to prove that characteristic function of x plus a by b. Now here on RHS side, substitute y is equal to x plus a by b. We get RHS term is expectation of e power j omega into x plus a by b. So this exponential term is written as e power j omega x by b into e power j omega a by b. So using property of the expectation, the RHS term of this equation is written as e power j omega a by b into expectation of e power j omega by b into x. From the definition of the characteristic function, the value of expectation of e power j omega by bx is pi x of omega by b. So therefore, pi y of omega is equal e power j omega a by b into pi x of omega by b. Next property, pi x of minus omega and pi x of omega are complex functions. So that is pi x of minus omega is equal to pi x of omega bar. Now coming to the proof. From the definition of the characteristic function, pi x of omega is equal expectation of e power j omega x. Using Euler identity, the expansion of e power j omega x is cos omega x plus j sin omega x. Similarly, expectation of e power minus j omega x is expectation of e power minus j omega x expression is using Euler identity cos omega x minus j sin omega x. So that is expectation of e power j omega x is pi x of omega. So expectation of e power minus j omega x is pi x of omega bar. Pi x of omega bar. So now here in this equation, the RHS term is written as expectation of cos of minus omega x plus j sin of minus omega x. Cos of minus theta, cos theta. Sin of minus theta, minus sin theta. So plus into minus, minus. So cos omega x minus j sin omega x is written as cos of minus omega x plus j sin of minus omega x. So using definition of the characteristic function, so expectation of cos omega x plus j sin omega x is expectation of e power j omega x. Using this expression, the RHS term of this equation is expectation of e power minus j omega x. So therefore, expectation of e power j omega x is pi x of omega. So similarly, expectation of j into minus omega x is pi x of minus omega. So pi x of minus omega and pi x of omega are complex functions. Next property, if a random variable capital X is symmetric function, that is pi x of omega is equal to pi x of minus omega. Now we are going now prove this property. By the definition of the characteristic function, pi x of omega is equal integral minus infinity to infinity e power j omega x f of x dx. So this is the continuous case of the characteristic function of the random variable. In this equation, substitute x is equal to minus y, we get pi x of omega is equal. So substitute x is equal to minus y, dx is equal to minus dy. So that is before minus, this minus 1 is that one. Dx is equal to minus dy. So therefore, pi x of omega is equal minus integral. So let x is equal to minus y. So now here what are the ranges of the x? X ranges are minus infinity plus infinity. Now here we are considering x is equal to minus y. Now calculate the ranges of y. So if x is equal to minus infinity, then y is equal to infinity. That is the lower limit. If x is equal to plus infinity, then y is equal to minus infinity. That is the upper limit. So the ranges of the y are plus infinity to minus infinity. So therefore, pi x of omega is equal minus integral plus infinity to minus infinity e power minus j omega by fx of minus y dy. But we know that for a symmetric even function, f of y is equal to f of minus y. So fx of y is equal to fx of minus y, and we also know that minus integral plus infinity to minus infinity function into dx is equal integral minus infinity to plus infinity function into dx, and applying this symmetric condition and that condition. What is that condition? That condition is minus integral plus infinity to minus infinity function into dx is equal integral minus infinity to plus infinity function into dx. So using these two conditions, this condition and this condition, the above equation, this equation is written as pi x of omega is equal integral minus infinity to infinity e power minus j omega y into fx of y dy. So from the definition of the characteristic function, the RHS integral term is pi x of minus omega. So therefore, capital X is the random variable. Capital X is a symmetric random variable. Random variable X is symmetric function. That is pi x of omega is equal pi x of minus omega. Next property is if capital X and capital Y are two independent random variables with the characteristic functions are pi x of omega and pi y of omega, then pi x plus y of omega is equal pi x of omega into pi y of omega. Next property is the function psi of omega is equal log of pi of omega is called the second characteristic function. So these are some important properties of the characteristic function of a random variable.